Merhabalar, Yıldız Teknik Üniversitesi Biyoteknoloji ve Genetik Kulübü Biyogen olarak hazırladığımız, bu sene üçüncüsünü düzenlediğimiz Astrobioloji Konferansı'nın ikinci gününe hoş geldiniz. Hepinizi aramızda görmekten büyük mutluluk duyuyoruz. Etkinliğimize başlamadan önce sizlere yapacağımız çekilişlerimizden bahsetmek isteriz. Parla Candle desteğinde gerçekleştirdiğimiz mum çekilişine katılım sağlamak için katılım formu oturum aralarında sohbet kısmında paylaşılacaktır. Ve YTÜ Biyogen Instagram hesabımızda paylaşılan çekiliş şartlarını yerine getirmeyi unutmayınız. Ek olarak oturum arasında oynayacağımız Kaut oyunu ile YTÜ Biyogen Instagram sayfamızda duyurulan ödül kitabımızı kazanabilirsiniz. Kaut zamanını takip etmeyi ve katılmayı unutmayınız. Şimdiden bol şans dileriz. Şimdi sizlere günün programını özetlemek isterim. Konferansımız bugün toplam 4 oturum olmak üzere saat 13.00'dan 17.15'e kadar sürecektir. Oturumlar arası 15'er dakika molamız olacaktır. Etkinliğimize dair katılım belgesini almaya hak kazanabilmek için oturum sonlarında paylaşılan ve aralarda geçen QR kodları ve link bağlantılarından oturuma katıldığınızla dair formları doldurabilirsiniz. Katılım belgesi alabilmeniz için en az 6 oturuma katılımınız gereklidir.
Esteemed participants, greetings. Welcome to the Astrobiology conference organized by the Biotechnology and Genetics Club, Biogen of Yıldız Technical University. We are honored to have each of you in attendance. Allow me to provide you with a succinct overview of today's program. The conference will unfold across 4 sessions, spanning from 13 to 17:15, with 15-minute intermissions between each. To be eligible for the participation certificate, we encourage you to complete the forms shared at the conclusion of each session, utilizing the QR codes and links provided during breaks. A minimum attendance of 6 sessions is requisite for certification.
Bugünün ilk konuşmacısı olan Sayın Şümse'yi yaşanılabilir dünyalar ve evrendeki yaşama ilişkin konunun sunumunu yapması için davet ediyorum.
I extend an invitation to Mr. Schulze, our inaugural speaker for the day, to deliver his presentation on habitable worlds and the search for life in the universe. Now you can start, Mr. Schulze.
Thank you first for having me. And yeah, I'll give you some of my insights or viewpoints on the search for habitable worlds and life in the universe. When you talk about habitable planets, the first question is, of course, what is habitable? And that will mean different things to different type of life forms. For example, this is a nice picture of Earth, and Earth is, of course, habitable for us, Homo sapiens. And we thrive at temperatures of 0 to 40 degrees C, 1 bar pressure, a solid medium, walking on the ground. We breathe oxygen, and we are heterotrophs, meaning we are eating the other guys. But there's also a great white shark, for example, who calls our planet a home. And you see the temperature and pressure is very different and lives in salt water and at the slightly alkaline pH as a heterotroph, also eats the other ones. But as a stark contrast, it is also home to Asiatus infernus, which is a lithotrophic bacterium that has its optimum temperatures at 88 degrees C and at an acidic pH and lives in water. So for all of those organisms, Earth is habitable. In fact, there's different kind of limits under which we expect life. The current hyperthermophilic record holder can grow at 122 degrees C. The survival range is probably still a bit higher at about 130 degrees C, but it's closing in at about 150 degrees C when some of the major building blocks of life disintegrate. So we don't know the absolute limit under which temperatures life is possible, but it's probably around 130 degrees C. On the lower limit, we know we had in our lab as well, we use Planococcus halograeophyllus that can grow still at minus 15 degrees C. There's some evidence for even a little bit lower temperature and reports of metabolic activity still quite a bit further down. The point is probably that metabolic activity in principle only ceases entirely when the aqueous cell plasma freezes, but otherwise there's always still something going on. So the lower limit is really not that greatly defined. There's a pressure range of life too. There are archaea from deep sea hydrothermal vents that survive pressures up to 89 megapascal. There has been experiments where this goes even much further down. So it's where the hydrothermal vents is, that's no problem anyway. Low pressure is a little bit more problematic, but there are several different species that still can survive at Mars surface pressures. So the pressure ranges don't appear to really limit life. Only sudden changes to it that are the most problematic for life, especially for larger life forms or multicellular life. One problem for life is, at least life as we know it, that uses water as its major solvent, is water activity. So the metabolism kind of stops at around 0.6. So it is really going there in this direction that there are still some new evidence with 0.59, but that's about it. Because if something is too hygroscopic, so attracting water and doesn't have enough free water, it doesn't work for bacteria. Just think about honey, for example. Honey usually doesn't go bad because the water activity in it is so low. There are some kind of exceptions to it, of course, again, too. And we'll see that, for example, one of my research sites is a pitch lake in Trinidad, and there's water droplets in oil. And the bulk active water activity is about 0.49, what's saying, okay, if you are in this kind of a material, you cannot have any life. However, we found life, and there's some droplets in the oil again, where this makes possible. Or when you have the water activities are fluctuating daily and seasonally, they can go below this threshold and then come up again, and life can still deal with it. And that is, for example, had our Atacama Desert, the Dry Limit of Life project, what was a huge undertaking. And here we found that was a major publication out at that you have transitory microbial habitats in the hyper-arid Atacama Desert. That means in certain time periods, the water activity was very much lower, and then the organisms were dormant, but then became active again at times when it's the water activity goes up. What we, however, always, or not always, quite often forget with extremophilic organisms that are not only bacteria. We have, for example, the crucian carp that can survive under low oxygen conditions for months. The Pompeii worm here that can survive at 105 degrees C. And what I would call Conan the tardigrade, that has temperature tolerances enormous, but actually this is only in the dormant state, where you can go to absolute zero till plus 150 degrees C, space conditions to 6,000 bar, up to 5,000 gray radiation tolerance, and then special adaptation traits like cryptobiosis and hydrobiosis, so that can survive nearly everything, really, in the dorm, but only in the dormant stage. So, so that is where we expect life on our planet, on our tree of life on Earth, which is incredibly diverse. So we have to distinguish things though between Earth similarity and planetary habitability. Earth similarity, you know, in exoplanet surveys is based on radius, density, escape velocity, and surface temperature. So, but planetary habitability has other factors, whether the planet has an atmosphere, whether it has something like plate tectonics, whether it has a suitable solvent. So I like to go a little bit on toward life as we don't know it, and look at some other planets or moons that may be habitable, but not very similar to Earth, like starting with Europa and Titan. So That could be in case of Europa, it's an ice-covered global ocean. The same will be maybe for Enceladus and some other icy moons. Then we look at Titan, which is a frigid world with abundant liquid hydrocarbons. And we'll look also at the rogue planets that are independent of their host star. So first we go to this ice-covered global oceans like Europa, and there we may even have something like hydrothermal vents and kind of complex life. And that may be a testing ground for the cosmic zoo hypothesis. I get to this in a moment. We could have familiar ecosystems with chemoautotrophic organisms that use different kind of pathways. Here using close to the icy surface, oxygen as major energy input. And here at the hydrothermal vents, using the reactions that you see at our hydrothermal vents too, that bacteria use there. But you could have something very different too. You could have something what I could call osmotrophs that could harvest energy from salinity gradients by coupling the water flux to a reaction that forms a high energy covalent bond. For example, it's energy favorable in the high salinity environment here to push out water molecules over here. You can get energy. And if you're in the low salinity environment, you can draw in water and gain energy that way. So under this dark conditions that you have in Europa's ocean, under this big icy surface, you could have the salinity gradients used for energy by organisms floating between the hypertonic ocean floor and the hypotonic water some distance above the ocean floor. And we can even calculate how much energy that would get. That would be, for example, 0.7 osmoles between the intracellular fluids and the surrounding environment as in teleosts on Earth. Teleosts are sharks, for example. But there's also bacteria that can take it a much stronger gradient. But if you calculate it out, then the potential energy yield would be about 0.006 electron volts per water molecule. So you could build 1 ATP molecules for every 50 water molecules that go one direction. So that would be in principle feasible, especially in a world without light. Let's get to Titan. Titan is one of my favorite planetary bodies, really. And life might have originated on Titans when it was warmer there and adapted then to the increasingly cold conditions. Titan is definitely a dynamic planet. You see here from the Cassini orbiter this image that with the flows, dark flows, here something like a lake as well. And the environment of Titan is very diverse. It's an active moon. Really, the only moon with an atmosphere, 1.5 bars. It has methane clouds. You have methane rain. You have cryovolcanic lava flows. And then you have these lakes here, hydrocarbon lakes. And then also ground ammonia water, groundwater. So there's a lot of different possibilities. But let's stay for the moment here on the surface more. And there could be life that uses exotic metabolic pathways. For example, the catalytic hydrogenation of acetylene. So that is acetylene plus hydrogen to methane, and that gives you quite a bit of energy. And all those compounds have been detected in the atmosphere of Titan. And, it's only difficult to do that in the lab, in our labs, because acetylene is an explosive under Earth conditions. But on Titan, it's very much colder, so it gives you enough energy to do something. Or you can get even more exotic. You could look at metabolic pathways involving radicals. So all those radicals have been found too, and that reaction gives you cyanamide, which is actually on Earth biochemistry used to glue amino acids together to proteins, or here HCN. So that would be another possibility. On Earth, again, radicals are usually not used as part of medical pathways. There are some exceptions, but usually not, because they make too much damage. They are too energy rich. But again, under the cold environment of Titan, which is lower than -100, it's about 97 degree Kelvin, there something like this would be feasible. If something lives in the hydrocarbon lakes, of course, that is a radar image over here. So you see there's quite a lot of lakes. And the environment may be very interesting because you have your hydrocarbon reservoir. You may have overheated volatile compounds. And so everything really what you would need for life. But if you have something living in the hydrocarbon reservoirs, of course, then the membranes has to be different, because our membranes work so greatly because they are polar to the outside, where you have the water, and in this case you have a hydrophobic compound outside, so they would have to be constructed differently, which is of course then exciting if life under those conditions exists, because it would be life as we don't know it, with a different kind of biochemistry. Or we could even imagine life on rogue planets that are, they don't have a host star anymore, but some of them have a really thick atmosphere and an ice layer, and inside, if they have enough heating inside, you could get energy from the high heat capacity of water and conformational changes. So if you have some kind of a black smoke on the ground, something that could work on Europa, for example, too, you can think of different kind of possibilities how you get energy inside, heating from the high heat capacity of water. You could even go more, this is not my idea, that was from Feinberg and Shapiro, but I find it kind of a great idea for thinking out of the box. Think about a planet around a neutron star, where the magnetic field is huge, and they come up with a system how a kind of genetic system could work without DNA, RNA, or any chemistry, just based on magnets. You have your randomly aligned magnets over here, which could confer information. Then there comes another magnet to it, and you can get some kind of a duplication of the line, a replicated chain, where those are only sensitive to direction, not to magnet size. So I find this intriguing. Of course, the thing is, if there's too much magnetic field, it could be then that getting remagnetized and things. So there would be some protection from the magnetic field. But in principle, you could store information and transmit information like that. So I find this still kind of amazing. There's also planets, when we think about habitability, that may be more habitable even than Earth. And in a recent paper with René Heller and Ed Guinan, we came up with some of the exoplanets that might be, where it goes mostly in the direction of the star type. So there's some other possibilities too. Of course, as the planet is a little bit larger, that would be beneficial. Or if you have more coastal areas where there's usually rich biodiversity. But one of the big things from the stellar part is that K-type stars seem to be more better for habitability, because they provide a long-lived and stable environments for 50 billion years or more. As you know, with our sun, it's increasing in output, energy output. And Venus used to be in the habitable zone, is not anymore. And Earth at some point will not be anymore, that there's, in a billion years, there's probably no complex life more possible on Earth. And in 4 billion years, there's no life anymore on our planet, because of our star type. And also G stars have a lot of X-ray and far UV emissions. That makes it more difficult too. Of course, it shows it's still possible because we are here. But anyhow, G stars are relatively short-lived and the habitable zone moves. And for M stars, there's another problem. There's also a lot of radiation at the beginning, and the planets are so close that there's a danger of tidal locking. So K-stars actually seem to be very good. So if a planet stays habitable long enough around a K-star, or a good G-star, for example, it likely contains also complex life. We think so because of what we put forward as a cosmic zoo hypothesis, that key innovations during the evolution of life on Earth have been achieved many times and using different biochemical pathways on the path toward complex life, yet with the same function. So the meaning, if a planet is stable, habitable and stable long enough, then at some of those planets will develop complex life forms. And it may be even the rule that it happens like that. So the question is that, do we live on a rare Earth or a cosmic zoo where that happens? And I elaborated on this hypothesis with my colleague William Baines in the book, The Cosmic Zoo, Complex on Many Worlds. And I thought it might be interesting for you. There's a Turkish version actually of the book too. Although since I don't know the language, I don't know how good the translation is. So if you're good in English, I would always recommend the English version. And the question we phrase there, are humans a galactic oddity or even freaks of nature? Or is that something what you would expect to develop on other worlds as well? So when we look at the different evolutionary transitions, there's different kind of models. And I hope you keep with me on that one, stay with me on that. The critical path model is that says that a major event or innovation requires preconditions that take time to develop. So it's basically the picture of a bathtub where you have the water running. At some point, it's all fulfilled and the bathtub overflows, and the evolution, the new innovation will happen. The random walk model is that the major event or innovation is highly unlikely to occur in a specific time step, and the likelihood does not change substantially with time. So that is basically the picture. You have 6 dice and you have to have all 6s. And as many times you throw it, the likelihood that this happens doesn't increase. So it may occur or may not. The many path models, which we believe most of the transitions follow, is that the major event or innovation requires many random events to create a complex new functions, but many combinations of these generate the same functional output. So that the picture is here that you have a poker game, and you can win with 4 aces, but you can also win with a royal flush. There's different ways how to get it and to achieve the transition. So if we can show that all the major transitions or key innovations are many path events, then we likely live in a cosmic zoo. That does not mean that we end up with animals or plants like on Earth, but organisms that in their functionality will be animal or plant-like. So the first major transition is, of course, the origin of life, where the conference about. And unfortunately, here we have to punt. I mean, you probably talked a lot about that too. And we don't know exactly how and things occurred. The idea is it happened between 4.2 and 3.5 billion years, probably more at 4.2 from recent evidence. And the main problem I see here that you have all 3 key functional carriers, genetic code, membranes, and proteins, or some precursor of that, have to work together in the same place at the same time. Otherwise, there is no living organisms, and they would likely disassemble again. So since our lack of understanding here we can't really say what kind of a path that is. So we have to punt, and I'll get back to this in a little bit. But the next major transition is the use of light. And photosynthesis evolved from mechanisms that were meant to protect organisms from light, and particularly from harmful UV radiation. And there's different ways how to do it. Most familiar, you are probably with chlorophyll-based photosynthesis, where you go the green plants outside. But light can also be captured with rhodopsins and carotenoids and turned into chemical energy. Actually, some of the organisms do it. Here you see on this picture here, you see some cyanobacteria of a quartzite that we turned around, and they're living actually underneath that. And bacterial rhodopsin-based light captures, for example, chemically completely different from chlorophyll-based capture, but a lot of bacteria use that. So this is definitely a many-path event because you can several ways how to utilize light. The major transition, another example is multicellularity. And there's many related branches of the eukaryotic tree of life that hold multicellular life form, which probably originated from colonial organisms. And there's laboratory proof that this can happen very quickly. But there's also these organisms like over here, where they change between like myxobacteria, between a single cellular and multicellular lifestyle. And so what is for us this kind of big step is for life is not such a big deal, really. Only for us, it seems to be a big step because we are obligatory multicellular. We cannot change to a simple cellular life back. But a lot of organisms actually can do that. And there's a lot of, in the tree of life, on the same branch, organisms that are multicellular, single cellular, or that can switch. One other major in transition I want to point out too is intelligence. And intelligence is not that rare. There's many different species at various times in Earth's history, such as cephalopods, birds, for example, like crows, cetaceans, that are whales, cephalopods are octopus, for example, and primates. So an intelligence is a needed asset for any predating species. I mean, you know, wolf, we have to be intelligent to get our prey. And there seems to be a selective pressure that a subset of organisms evolve intelligence. So what we can see, there's a lot of different intelligent organisms on our planet. However, technological intelligence seemed to have only evolved once, and that was with us. We do not know exactly why is that the case. There are some factors that seem to be critical for that, like the high dexterity in our hands, invention of fire, language, heat engines, our social, to be social as well. But again, since this only occurred once, as far as we know, we cannot say whether this is a many path or critical path or a random walk event. So if you want to summarize here up, and in the book it's much more detailed, there are many math processes can be basically shown for all major transitions, except two that are shown here, the origin of life and the rise of technological intelligence. So if the origin of life is extremely unlikely, then we'll live in a rather empty universe. But if not, and I mean, most of my colleagues at least believe we are not, then we live in a cosmic zoo, meaning there's animal and plant type of life around, but we don't know quite with technological intelligence. But let me come back to one of the major key things before. Why did it only happen once with technological intelligence on our planet? And that is indeed a big question. Because we had, this is a carnivorous kangaroo, 75 kilograms heavy, and you know, kangaroos are very have dexterity and social. And actually, so the troodon, look how the long arms and fingers and but they did not develop technological intelligence as far as we know. So why is that not the case? If we would actually encounter, how would we react to it? Technological intelligence, that's a bear, right? Bears are dangerous and they can kill humans too. Yet we like to make teddy bears out of it, child's toys. However, if we have a spider now here, The spider people are much more scared of, even though are usually harmless. The thing is that we are feeling much more closer to something what is related to us. And if we would now encounter aliens, we would be not related to it at all. So we probably find them disgusting. So what kind of alien would we likely meet? It would be probably not something like here ET, but it would be something like this, more very strange, very alien, and something that may not quite attracted to. So, and if we would meet someone, how would they be? And so there is a point to be made that intelligence is needed. Who is the most intelligent of those organisms? Well, and the cows graze not that much. Snakes, they have a lot of venom, but they're not very intelligent. Here we have a leopard, and a leopard, of course, has to be strong, has to kill its prey, and has to get it, so it has to be intelligent. But I would argue that the wolf here is even more intelligent, because not only does he hunt and has to get its prey, and the prey is often quite bigger than the wolf itself, but during the hunt, it has to also communicate with its fellow wolves. So you have to anticipate the future. So if we actually find some aliens out there, that would be probably more like a social predator. You know? So there are certain dangers in with that too as well. So that leads me to the family paradox. Although certain things we might have expectations, we haven't found any. So why are they not here? I mean, if we put here the numbers into the Drake equations, a lot of you are probably familiar with it. Usually people come up with pretty high numbers of different life forms in our galaxy. But one of them is fraction of those Earths where life developed. So if the origin of life is very rare, then of course the whole thing goes, one term goes to zero, the whole thing goes to zero. So it doesn't really kind of inform us. But given all the different planets out there and this huge universe, the question is still, why haven't we found any? And if we think about this Von Neumann probes, so let's say there's an ETI's extraterrestrial intelligence civilization interested in space exploration. It should only take about 4 million years for them to have explored the whole galaxy if they use this kind of probes. Self-replicating probes. They don't have to be that complicated. Flying at a speed of 1/40th of light velocity, you can make the calculations. Then it takes 4 million years. But we haven't seen any of those. And actually, we do not have any conclusive evidence. So what is the problem? Why haven't we been contacted? So one idea is that we are perhaps living in a human zoo or designated nature preserve, that the aliens are conscientiously hiding from us because they don't want to interfere. For the Trekkies of you, it's kind of like the prime directive. So that would be one possibility. One intriguing one is that we and our universe around us are part of an elaborated computer-generated hologram. Again, that was featured in Star Trek with Ship in the Bottle, Professor Moriarty. There would be some observations that could possibly support such a notion, like the observer effects in quantum mechanics, which is, we're living more in an information universe than a physical universe. Information entropy, the radiation around black holes. And that's an anthropogenic principle, and the natural constant of the universe is just like that, that we can live here. So it's something that we should probably not easily dismiss. Some of the things, of course, that makes us a bit more modest, if you think about it, maybe we're just not advanced enough for aliens to contact us. Let's face it, if we discover a new worm species in the Amazon, we are not trying to communicate with them either. Perhaps advanced civilizations self-destruct at critical junctions in their development. But that doesn't seem to be, it's not satisfying either, because you wouldn't think that all of them do. Maybe we have to look from a different angle. How would we detect intelligent extraterrestrial life? We usually use traditional SETI initiatives with radio frequencies. Nowadays, there's also additional frequencies to it added, but so far nothing. We're looking really for energetic emissions that are neither highly regular, like from a pulsar, nor highly random. But if you land somewhere and see structural complexity, something like this with a big autobahn or highway, then of course that is something. Or I mean, even more if we find here kind of like a rover. I mean, we leave our trash on Mars as well. So if someone comes later and sees this, then okay, that must have been from intelligent life. So if we explore other places as people, then and find something like this, then we know at least there was intelligent life, because something like this could not self-assemble. So nothing so far. So what could be wrong? Perhaps the origin of life is hard and statistically very unlikely. It happens so likely that in fact we are alone, or there are only a few other instances when it happened in the universe. So it's definitely not as we imagine with the Miller-Urey experiments. We have our primordial soup, we put some lightnings inside some meteorites, and voila, the amoeba crawls out of it. It doesn't seem that easy. And it does give us a sort of thought too that, we still haven't figured it out. So that could be, of course, one of the answers. But on the other hand, life really evolved as soon as it could on our planet. And it is like water-filled bags, seem to formed also in the ocean or in water. So you wouldn't think that it is that difficult that it could be happen elsewhere too. So we simply don't know in principle. So that's where the idea of the great filter came. So the great filter meaning, okay, that's where it stops for most of life in our universe. So it may be at the origin of life, which would be quite sad because we would be in a rather lonely universe. Or it may be towards a step toward technological intelligence. I don't think it's anywhere in between, origin of life or there. Or most scary, it may be right in front of us, that something happens where it takes out most or nearly all, or really maybe all of intelligent life. Given that the universe is so well suited for life, shouldn't be there much more evidence of life around us? Of course, you can argue now we are still in the baby steps of technology. But I think the Fermi paradox tells us something important about life and the universe. Well, the question is only what? Ian Crawford and I did make in a recent article that came out in December 2023 in Nature Astronomy and suggested, well, it's either the Zoo hypothesis that I introduced here before, or there is really hardly anything out there. So if you're interested, please read it. If you can't get access, just send me an email. I sent you the paper. So the conclusions of my talk, or what I like you to take you with me, is that biology can certainly be more diverse than we observe on Earth. And there's already lots of diversity on Earth. Life and environment are intrinsically intertwined. One doesn't go without the other. So you have to really know both to understand it. And biology may be more complex than we anticipate, and more complex on other worlds too. And one thing is for certain, when searching for life, we have to think outside of the box. The universe seems to just be stranger than we think. And if you like to know more, I'd like first to point out my website, searchforlifeintheuniverse.com, where I have a lot of blogs on especially as new discoveries too, and discuss them there. And then obviously my book, The Cosmic Zoo, Complex Life on Many Worlds. If you like it more academic, it's Life in the Universe, Expectation and Constraints, the third edition. If you like catastrophes, mega catastrophes, this is here more the popular science version of that book. and I couldn't help myself to still write a science fiction novel. So thank you very much for your attention, and I'm happy to answer any questions that you have.
Thanks for your presentation, Professor. We have two questions to you. We know that ATP is used in metabolic processes necessary for life. What kind of energy source can creatures developing possible life cycles on other planets use?
Well, it is that is difficult to predict. It depends. The whole biochemistry is the kind of a machine. It depends what is used for that. But I mean, even on our planet, some organisms use GTP or CTP. So there's already in that way, there's some kind of diversity. Actually, the phosphate from it is really a big puzzle. And it would be really good if some people could address that. Because the phosphate, I mean, obviously you have it in the DNA too. You have it in ATP, and you have also in a lot of lipids, you have that too. So it seems to be critical. And in some way, when I give a talk, I always argue, you know, we would better be called not carbon-based life, but phosphorus-based life. Because if you compare how much carbon is to the natural background, that is actually less than if you compare how much phosphorus is in us or in any living form than compared to the natural background. So we are much more phosphorus enriched than carbon enriched. And without the phosphorus, actually life as we know it, or life on our planet, would not be thinkable. So, so the phosphorus is critical.
Okay, and the other one, what kind of points are taken into consideration when searching for biosignatures on other planets?
Well, there's it depends first how you search for, right? I say always, as an astrobiologist, you have to get in close and personal. So you actually want to land and just sample and look at it, you know. And I would like, if we go to Mars and look for life, that we actually take a microscope with us and look, you know, because unless the microbe is waving back to us, nobody will believe you. You know, you get some kind of markers and say, okay, yeah, maybe that's consistent. But then there's 100 other ways how to get it. So that is one point. Now, there's a lot with the exoplanets that you look for biosignatures in the spectrum also. And I think that is very difficult to make a conclusive argument that this is really life, you know, because especially if you have trace compounds. Let's say it like this. If I would find some compound like chlorophyll or rhodopsin or something that does photosynthesis in huge amounts on a planet in the planetary atmosphere and can detect it, which is challenging at this time. I don't think we can do it yet. Then I would count that, okay, that is a convincing biosignature. But anything less than that, you know, carbon dioxide is a dead compound, basically. If you find some carbon dioxide, it doesn't tell you much. If you find water, well, that's everywhere too, you know. Even if you find, you know, oxygen also, it doesn't tell you much either. It could be something the case. Think about the moon Europa. You have a major asteroid impact on it, right? Then you volatilize the whole ice. The hydrogen of it escapes into space and you actually have an oxygen atmosphere, but it has nothing to do with life. So there's always so many different possibilities then. If you have then oxygen and methane at the same time, like on our planet, okay, that goes closer to it, but you can come up with inorganic explanation for that too. So the only thing what I really would find convincing is some kind of compound, complex compound like chlorophyll, with which you can do photosynthesis in major amounts on that planet or in the planetary atmosphere that you can detect on. It would be on the planet, not in the atmosphere, really. And then that I would find convincing. But anything else like this, not really. Unless you get a signal, you know, and you have intelligent communication, of course, that works too.
Thanks for your answers.
You're welcome.
Sayın Schulze'ye sunum için teşekkür ediyoruz ve kendisi adına Tema Vakfı'na bağış yaptığımıza belirtmek istiyoruz. Sertifikasını mail üzerinden kendisine göndereceğiz.
Our sincere gratitude to Mr. Schulze for his presentation, and we are pleased to announce a donation to the Tema Foundation on his behalf. His certificate will be dispatched via email.
Okay, thank you very much.
You're welcome.
Okay.
Değerli konuklarımız, bir sonraki oturum için 45 dakika ara verilmiştir. İkinci oturumumuz saat 14.30'da başlayacaktır. Ayrıca chat kısmında paylaştığınız formu doldurarak çekilişlerimize katılabilir. Katılım formlarınıza da oturuma katıldığınızı belirtmek için yine chat kısmında ve aralarda paylaştığımız QR kodlardan ulaşabilirsiniz.
A 45-minute intermission has been allocated before the commencement of the next session. The second session will commence at 14:30.
Okay. Well, thank you very much.